Section: Introduction. In this section, we introduce our approach to tackle the computational challenges in reinforcement learning for large language models, LLMs. We start by reviewing the Standard Group Relative Policy Optimization (GRPO) algorithm, outlining its structure and computational needs. Next, we present our framework, PODS, Policy Optimization with Downsampling, which strategically selects rollouts to maximize resource use during both the inference and policy update phases. We then develop our max-variance downsampling method, which effectively captures diverse signals from both high and low reward examples. We demonstrate that this method offers a practical and efficient solution, enhancing real-world implementation. Our framework maintains the key benefits of GRPO while improving the use of computational and memory resources in distributed training settings. Section Summary. In this section, we introduce our approach to enhance the efficiency of reinforcement learning for large language models by implementing the PODS, Policy Optimization with Downsampling, framework, which strategically selects the most informative rollouts for policy updates. This method addresses the computational asymmetry in standard algorithms like GRPO, maximizing resource utilization during both inference and policy update phases while improving training efficiency. Section: Inference Phase. In this section, we describe the inference phase of our approach. We denote the policy parameterized by theta as pi_theta, which helps us determine the probabilities of the next tokens based on the previous tokens in a sequence. For a given input prompt, such as a math problem, we first generate a set of n rollouts, represented as a sequence of outputs, by sampling from pi_theta. Each rollout is a potential solution that excludes the prompt. We then evaluate each rollout using a reward model, which gives us a score for the quality and correctness of each output, resulting in a reward vector. Next, we calculate normalized advantage estimates from these rewards. The advantage for each rollout is computed by taking the difference between the reward and the mean reward, divided by the standard deviation of the rewards. In the policy update phase, after we have the advantages, we update the policy by optimizing the GRPO objective. For each rollout, we calculate a loss for each token position, using a fixed version of the policy for importance weighting. This loss function reflects a learning principle where we are cautious in increasing probabilities for high reward tokens while allowing more significant reductions for low reward sequences. We introduce the PODS framework to separate the inference and training phases of GRPO. Instead of using all generated rollouts for policy updates, we generate many rollouts in parallel but only train on a smaller subset based on a downsampling rule. This method allows us to take advantage of parallel computation during inference while minimizing communication and memory costs during policy updates. The downsampling rule takes the generated rollouts and their corresponding rewards, along with a target size, and outputs a subset of indices indicating which rollouts to keep for the policy update. We then compute advantage estimates using only the selected rollouts. We propose several downsampling strategies. The random downsampling method selects indices randomly, maintaining the original distribution statistical properties. The max reward downsampling method focuses on the rollouts with the highest rewards, allowing the model to learn from the best examples. To address the limitations of max reward downsampling, we introduce max-variance downsampling, which selects the most diverse and informative rollouts based on the reward distribution. This method aims to maximize the variance of the rewards, capturing a broader range of performance and providing stronger learning signals. We demonstrate that the optimal subset for max-variance downsampling consists of the highest and lowest rewards, ensuring we capture both successful and unsuccessful reasoning paths. We also provide an efficient algorithm for this downsampling rule, which can be computed in a reasonable time frame. While we could further optimize the time complexity, we choose to keep it simple for practical applications. Section Summary. In this section, we describe the inference and policy update phases of our GRPO framework, where we generate multiple rollouts from a policy, evaluate them using a reward model, and compute advantage estimates for policy updates. We introduce the PODS framework to decouple these phases, allowing for efficient downsampling of rollouts based on various strategies, including random, max reward, and max variance selection, to enhance learning while minimizing computational overhead. Section: Architectures, Benchmarks, and Baselines. In this section, we evaluate our method's effectiveness by conducting experiments on the GSM-8K dataset. We compare our downsampling approach with the original GRPO method over the training period. We use the Qwen 2.5-3b instruct model as our base and fine-tune it with both GRPO and GRPO pods, applying the max variance downsampling rule on the GSM-8K training set. We assess model checkpoints on the test set every 100 training steps. For training, we fine-tune the base model using LoRa with a rank of 64, a learning rate of 5 × 10⁻⁻⁶, a weight decay of 0.1, a maximum gradient norm of 1.0, and a constant learning rate schedule with a warm-up ratio of 0.01. We set the maximum sequence length to 1024. For GRPO, we use 16 rollouts. For GRPO pods, we generate 32 rollouts and select 16 for policy updates. We implement a rule-based reward model that scores each rollout based on correctness and format. We also omit the KL divergence term from the GRPO objective, as it is unnecessary for reasoning tasks. Each algorithm runs 8 times with different random seeds, and we evaluate each saved checkpoint on the test set 5 times, reporting average accuracy with standard error. Our results, shown in the figures, indicate that our downsampling method outperforms the original GRPO method given the same training time. We find that GRPO pods with max variance downsampling consistently surpasses GRPO as training progresses, with the performance gap becoming more pronounced over time. This confirms that our pods framework effectively enhances GRPO's performance on reasoning tasks.